You ever watch a sprinter just explode from the starting blocks? I mean, it's this incredible display of power and speed, right? And it's all over in a flash. But what's amazing is that in those, 10 seconds, a whole story unfolds. And it's not just a story about sports, it's a story about the fundamental laws of physics. So let's get into it.
Because that's exactly what we're going to do. We're going to break down every single phase of a 100-meter dash to really get our heads around the core ideas of motion, things like position, velocity, and acceleration. We're basically turning the running track into our own personal physics lab.
And to do that, we're actually grounding this whole thing in a real-world problem from an AP Physics workbook. So this isn't just some abstract theory. It's a simplified but pretty accurate model of how elite athletes actually move. They don't just run. They strategically manage their acceleration and their velocity.
And here's how we're going to break down that strategy. We'll follow the race from start to finish. We'll start in the blocks to define position, then talk about that explosion of acceleration, then look at the phase of constant velocity, and finally, we'll see how one simple graph can tell the entire story of the race.
All right, first up, the starting block. Before anything happens, before a single muscle moves for the race, we have to establish our starting point.
You know that moment of stillness? It's incredibly important. The tension is building, the crowd is silent, and in physics terms, everything is at a standstill. We're about to see a massive change, but first, we have to define that where.
And position is probably the easiest of these ideas to grasp. It's really just a coordinate. For our race, the starting line is position 0. That's our origin, the point from which we're going to measure everything else.
And this right here illustrates it perfectly. So on this graph, the vertical axis is velocity. Think of it as speed, and the horizontal axis is time. Now look right there at the origin, the point 0, 0. Time is 0, velocity is 0. The runner is at their starting position, totally motionless, just waiting for the signal.
Okay, now for the fun part. Let's see how we go from 0 to 60. Well, not 60, but you get the idea. This is where the physics gets really exciting. Bang! That one sound changes everything. I mean, in an instant, that runner goes from a state of complete rest to a state of incredible motion. Their velocity is definitely not 0 anymore. It's changing, and man, is it changing fast.
And that change in velocity? Well, that's got a name: acceleration. See, it's not about how fast you're going, it's about how quickly your speed is increasing. A sprinter's whole goal in those first few seconds is to maximize their acceleration, to generate as much force as they can to get their velocity up.
And what's so cool is how that physical explosion is shown so cleanly right here on our graph. You see that steep line sloping upwards? That's it. That's our acceleration. The line is going up, which means velocity is increasing over time. And the steeper that line is, the faster their speed is picking up. The runner is gaining speed at a nice, constant rate.
But, that massive acceleration can't last forever. The human body has its limits. So now the runner transitions into the next phase of the race. This usually happens a few seconds in. The runner's upright, their stride is smooth and powerful, and they've basically hit the maximum speed they can possibly sustain. They're not speeding up anymore. Now it's a battle to just maintain that speed. And that brings us to velocity. We've kind of been talking about it this whole time, but this is where it really becomes the star of the show. At this stage, the runner's velocity is at its peak. And this is the important part. It's now constant. The change in velocity has dropped to 0. If we look back at our graph, you can see this perfectly. The line just goes flat. A horizontal line on a velocity time graph has a slope of 0. And what did we say the slope was? Acceleration. So a 0 slope means 0 acceleration. The runner is just flying down that track at a constant, incredible velocity. So we have all the pieces now. Let's put them all together and see the entire 100-meter dash as this single elegant story, told by a simple graph.
And there it is. The whole race, from start to finish. You can literally see the initial burst of acceleration, that long stretch of them maintaining top speed, and then even the deceleration as they cross the finish line and start to slow down. It's a whole narrative, just in 2 dimensions.
So, knowing how to read this is everything. The upward slope, that's the runner speeding up. The flat line, that's them hitting their top speed, just holding it constant. And the downward slope at the end, that's them slowing down, decelerating. But here's the part that's just so cool. If you were to calculate the total area underneath that whole shape, you'd get the exact distance the runner traveled. Think about it for a second. Area is just height times width, right?
Well, on our graph, the height is velocity and the width is time. And velocity times time, that's distance. So for this race, that area adds up to exactly 100 meters. How awesome is that?
You know, it all seems kind of complex, but when you really boil it down, the fundamental physics of motion is about one simple, powerful idea.
And this is the big takeaway. It's all about how things change. If your position is changing, you've got velocity. And if your velocity is changing, you've got acceleration. Each idea is built right on top of the one before it, all the way from the stillness of the starting block to that explosive finish.
So, I'll leave you with a final thought here. We've seen the graph for a short, explosive burst of power. But what about a race of pure endurance, like a marathon? What would that graph look like? How would the acceleration, those periods of constant speed, and all the little changes in velocity tell the story of a 26.2-mile journey? The physics is exactly the same, but the story, well, that would be very, very different.